Hi, class. Today we're going to talk about reviewing our exponent rules. First of all, let's recall exponents. Let's say we have a power like a to the power of m. This entire thing is called a power. And the power is made up of two different parts. A power always has a base, that's the number at the bottom, and a number at the top, which is the exponent. Now, this would give us a number if we decided to expand it. But sometimes we prefer to keep things in power form because the number can be a very large number. So, one of the purposes of having an exponent is to represent large numbers, and it's a short way to write it. Now, another reason we do use powers is we use this to express repeated multiplication. And as I said before, as a shortcut to represent very large numbers. Now, when I say this is repeated multiplication, this is the repeated multiplication of the base. So let's clarify the base. The base is the number that is directly in front of the exponent. Let me say that again. It's not just the number. It could be the number, the variable, or term that is directly in front of the exponent. And I put the word directly in capital letters because when I say directly, it means the only one thing that's in front of the exponent. Let's look at this. So let's say I had a to the power of m versus 2a to the power of m versus bracket 2a to the power of m. So this one, the thing that is directly in front is the a. So the base here is a. In our second example, I have 2a to the power of m. Once again, the base is still just a because the 2 is not directly in front of the exponent. Now, on the other hand, when I have bracket 2a to the power of n, my base is now 2a. And the only reason that this is part of the base is because I have a bracket. And the bracket shows that the 2a is together. So this entire term is considered the base for the power m. All right, so let's do a couple of calculations. I have the question 2 to the power of 3. let's compare that to negative 2 to the power of 3 and compare that to negative 2 to the power of 3. Now, these three are similar to what we've done up here. So, our first question, 2 to the power of 3, we have a base of 2. So, that means this is 2 times 2 times 2. Negative 2 to the power of 3. Now, it looks like negative 2 is the base, but because there is no bracket, the negative sign is not considered something that is directly in front of the exponent. And so our negative is like a coefficient. So since it's not part of the base, it's like we have a coefficient of negative, and that's being multiplied by 2 times 2 times 2. Now, in our last question here, negative 2 in a bracket to the power of 3, our base is negative 2. And so our question, when I expand it, would become negative 2 times negative 2 times negative 2. Okay, our first exponent law, the product of powers law. Now, when we talk about the word product is a fancy way to say multiply. So this is about multiplying. When we have x to the power of m times x to the power of n, it can be simplified to x to the power of m plus n. So let's write that in words. So the exponent law says if there are two powers with the same base are multiplied together, then we can add the exponents together. Okay, let's do a couple of examples to illustrate this. We have 8 to the power of 4 times 8 to the power of 10. Our base is 8, and this is multiplying. So we can take the exponents, and multiply them together. Or sorry, what am I saying? Because the bases are being multiplied, we can add our exponents together. So we have 8 to the power of 14. Second question, we have bracket 5x to the power of 8 times 5x all to the power of 3. Now, because we have the same base and the base is 5x, we can add our exponents together. So we put 5x in a bracket to show that the entire thing is the base, and we're going to add our exponents. Okay, now our last example here, we have 4m cubed times 4 squared m to the power of 7. We've got two different bases here. So let me indicate that we have the base 4 and we have base m. So since we have two different bases, we are going to apply the product rule to both of these. First, let's take our 4. 4 has an exponent 1. It's implied and it's not written. So when I have the 1 and the 2 here, that gives me 4 to the power of 3, and we have m to the power of 10 because we're taking our 3 and we're going to add it to the 7. Okay, so these are examples that illustrate the product rule. Now I'm going to do two anti-examples. Anti-examples are things that are not examples, but these are things that I often see in students. So I'm going to do an anti-example to show why these don't work. Okay, our first question here, we have 5x squared plus 5x to the power of 6. This does not equal to 5x to the power of 8. Why is that the case? Now, to prove that these don't work, we need to go back to the definition and see what part of the definition it fails. So the definition of the power law or the product rule says that if we have the same bases and powers, so let's start this again. Okay, let's go back to the exponent law. If two powers with the same bases are multiplied together, then we can add the exponents. Now we do have the same base, but we notice that these are not being multiplied together. These two powers are being added together. And because they're being added, we can't apply the rule to add the exponents. Right, let's look at our second example. 4 or a to the power of 4 times b to the power of 5 does not equal ab to the power of 9. Why is that the case? So once again, let's check our rule. If two powers with the same base are multiplied together, then you can add the exponents. We've got two different bases here. So even though they're being multiplied, we can't just add the exponents. Right, the next rule that we have, Quotient of Powers Law. The word quotient is a fancy way to say division. And so this is going to be about dividing powers. Here it says x to the power of m divided by x to the power of n is equal to x to the power of m minus n. So in summary, our exponent law states when we have powers with the same base are divided, the exponents can be subtracted. Right, so let's look at a couple of these examples here. 3 to the power of 30 divided by 3 to the power of 16. We have division and we have the same bases. So I can take 30 and subtract 16. So 3 to the power of 14. Second question here. 4 to the power of 3, m to the power of 13 is all divided by 16 m to the power of 7. Now we notice that there is only m that is the similar base right now. So If I look at 4 to the power of 3 and 16, you should ask yourself, is there any way that we can make 16 a number with a base 4? Now we know that 4 to the power of 2 is equal to 16. Now, if we rewrite that, then we would have all the numbers with base 4. So let me rewrite the question. 4 to the power of 3 m to the power of 13 divided by 4 to the power of 2 m to the power of 7. Let's apply our quotient rule to both the powers with base 4 and powers with base m. So I have 4 to the power of 1, and I'm not going to write the 1 because the 1 is an implied exponent, and m to the power of 6. I took 13 and I subtracted 7. Right, the last one that we have, x to the power of 7 divided by x to the power of negative 8. This is a straightforward quotient rule question, but we have to remember that when we're subtracting exponents, our integers we still have to take our integers into consideration. So I have 7 minus 8. So when I have 7 minus 8, the two negatives will give us 7 plus 8. And simplified, we have x to the power of 15. So be very careful if you're subtracting a negative number. Now let's do a couple of anti-examples. Anti-examples, once again, are examples that don't work. Okay, our first one here, I have 5x to the power of 6 divided by bracket 5x all to the power of 2. This doesn't equal 5x all to the power of 4. Why is that? Let's go back to our rule. The quotient rule says that when the powers of the same base are divided, then the exponents can be subtracted. Well, we've got two bases going on right now. I have a 5 and an x, whereas in my second one, the entire base is 5x. So I need to simplify this until I have 5 and x as two separate bases. We can't combine the bases 5 and x with 5x together. Okay, so we will be able to do this question, but it does not end up like this. Right. The second part here, m to the 15 divided by m to the negative 8. It doesn't equal m to the power of 7. Why is that the case? Well, we know that we have to subtract the exponent because the rule says that exponents can be subtracted if the bases are the same and divided. So because that is the case, I have m to the power of 15 minus 8. Now, when I simplify this, my two negatives become a positive. So I have m to the power of 15 plus 8, which would give us m to the power of 23. And so this doesn't work because we didn't subtract here. This is subtraction, and that gives us a different answer. Right, our third main exponent rule is the power of powers. So, example of power of powers, or I guess writing it in summary, we have x to the power of m all to the power of n. So, you see this power has an exponent. So, power has a power. Together, that becomes x to the power of m times n. Another way we could write this is if we have x over y all to the power of m, this would give us x to the m over y to the m. Or another way we could say it is if I have axy all to the power of m, this is equal to a to the power of m, x to the power of m, and y to the power of m. So the exponent law here states that a power of a power can be simplified by multiplying the exponents together. Now, here's the little note. We have multiple bases inside the bracket. So if we have more than one base, then our exponent just needs to be distributed to all of the bases. And we call that the distributive property. Multiple bases. So when I say the exponent is applied to each base, it's you could also say the exponent is distributed to each of the bases. Okay, so let's do a couple of examples here. The first one, 2 to the power of 6 all to the power of 3. This is classic power law example. So I have a base, I've got two exponents. I'm going to multiply the exponents together. So I have 2 to the power of 18. Second example, x to the power of 4 divided by y to the power of 2. All of it is to the power of 3. Now remember, if I have more than one base, my exponent has to be distributed to each of the bases. So we're going to use the power law for my numerator and for my denominator. So our first one, we have x to the power of 12, all divided by y to the power of 6. Last example, bracket 2xy to the 5, close bracket, all to the power of 3. So the 3 is going to be applied to all of the bases inside the bracket. We have 2 to the power of 3 because without an exponent, we have the implied 1, x to the power of 3, and y to the power of 15. Okay, let's look at a couple of anti-examples. So if I have 3g to the power of 6, this is not equal to 3 to the power of 6g to the power of 6. Why is this not the case? The 3 is not directly in front of the exponent. And because it's not directly in front of the exponent, this is just considered a coefficient. And the exponent is not applied to the 3. Right? Our second example, m to the power of 5 divided by n, all to the power of 2. This is not equal to x to the power of 10 over n. Why is that the case? Well, according to the distributive property, we have to apply the exponent to every base inside our bracket. So we can write the 2 must be applied to all bases. So the real answer is going to be m to the power of 10 all divided by n to the power of 2. Power of 0 law. Y to the power of 0 is equal to 1. What that says is all powers with exponent 0 is equal to 1. Now, there is one caveat. Our base can't be 0. Okay, so let's do two examples. 2 to the power of 6 is equal to 0. Our entire base is applied to the 0. So our final answer is a 1. Next example, we have 3m to the power of 0. Well, here's a note. Remember the exponent 0 is only applied to base m. Because the 3 isn't directly in front of it, the 3 is a coefficient. This is the number that's going to be applied, or this is the number that's going to be multiplied to 3. 3 is the number being multiplied to m to the power of 0. So let's simplify it. We would have 3 times 1. Because we know that m to the power of 0 is equal to 1. Our final answer is 3. Okay, here's an anti-example. Negative 3 to the power of 0 is not equal to 1. Why is that the case? The negative is not a part of the base. I mean, we could rewrite the question. Negative 1 times 3 to the power of 0. And so that would change how we look at it. Negative 1 times positive 1. Final answer is negative 1. The last power rule that we're going to review is the negative powers law. The negative powers law says that if I have a power that is negative, we can make it positive by flipping the base. So if I have x divided by y, and this is to the power negative n, it's equal to y over x to the power of n. So our exponent law. All powers with a negative exponent can have a positive exponent when you take the reciprocal of the base. So the word reciprocal means to flip it. So we have xy, we're going to flip it. Our denominator becomes the numerator. Our numerator becomes the denominator. Same thing here. So let's simplify this. Negative 6 to the power of negative 3. We can flip it so that negative 6 now becomes 1 over negative 6. And this is all to the power of 3. Another way you can write it, you could write negative 1 over 6 to the power of 3. Okay, part B, 3 over 2 to the power of negative 4. Let's make this positive by taking the reciprocal of the base. So we have 2 over 3 to the power of 4. I want you to try some of these questions on your own now, and then in the next video, I will take these questions up.